Hello guys, you're welcome back to my channel, and please let me remind you, if you like the content of my channel, I want you to leave a like on the videos that I make, and then please subscribe to the channel, and turn on post notification, um, so that you just anytime I post a video, you're just gonna get the notification that I have posted something. Okay, so now in today's video we're going to try and then solve this special type of first order partial differential equation. Okay, and this is very useful because we will be using that idea to solve the transport equation. Okay, so let me not waste much time. I don't really want to be talking that much, so let's just get straight into it. So this partial differential equation I have here, I can write it as AB ux uy equals 0. Okay, so I can write it as an inner product. Is it really an inner product? Yeah, kind of these two. Okay, then what I'm going to do is that I'm going to call AB a vector v. So I'm going to let v be maybe AB. And note, you are only proving, you are going through the steps to, you are developing a certain solution, or a solution as a function of something which can just be used at any point. Anytime you see an equation like this, you should know how to apply it. Okay, you don't have to go through all these steps again to find a solution, but it just becomes straightforward. Okay, so v be that, and then what do you make of this? We know that the ux uy here is just nabla u. And how do you call this? This is the gradient of u. Okay, yes. Now this implies that I have a v nabla, that's a vector, so I can now do the dot product, or v nabla u. Okay, and that should be equal to 0, right? Good. If I have something like this, what does this represent? I just want to ask a question. What does this represent? It represents the directional derivative of u, right, in the direction of v. Okay, so this is an equation which is very, very crucial. So what does it tell us? It means that the directional derivative of u in the direction of v is 0. It implies that u has to be a constant. It's constant. Because if the derivative of something is 0, it means that thing is a constant, right? So now we expect that u of xt is a constant. So now there are two approaches. There are two ways we can come up with that function, or that constant. Now what we want to have is, we want a combination. Oh, sorry, this is supposed to be y. We want a combination of x and y, or a function of the combination of x and y, which will always be a constant. Okay, it is always going to be a constant, and that is what we are going to look for. So there are two ways. We have the geometric approach, and then the next one we have the coordinates method. We are going to talk about both of them today. So this video may be a bit lengthy, but that shouldn't be a problem. So on my xy plane, I have this vector v. So this is my vector v at an angle phi. Then I'm going to call this one an x. That is my s coordinate, my y coordinate of this point. And then now this x and y are actually variable. They can move anywhere you want. Okay, then I'm going to pick a constant, or a point, an actual point here, which has the coordinate x0 y0, x0 y0. Okay, so what do we expect? We expect that the gradient is 0. The gradient is 0. So we expect that y minus y0 divided by x minus x0 to be, we expect this to be equal to b divided by a, because BAB is this vector. That's the vector here. And the gradient of that should always be equal to that. Okay? Yes. So, if that is the case, we then have A multiplying Y minus Y naught being equal to BX minus X naught. Okay? And then what do we have? We have AY minus AY naught being equal to BX minus BX naught. And then we consider we have AY minus BX. Or let me just, yeah, okay. It doesn't change anything. BX being equal to AY naught minus BX naught. Now what is this? This is a constant, right? So this means that the combination of x and y, which will always yield a constant, is AY minus BX. So it implies that u of xt is going to be a function of this combination of x and y, which is always a constant. So that's a certain constant, and that constant is AY minus BX. Okay? It's a bit rough, but it makes a lot of sense. Okay? Yeah, so it means that if I'm given, why do I keep using t? Is why. So it means that if I'm given any PD of this form, all I need to do is just plug in, I need to just find f of c, or a function of a constant, and that constant is always going to be the AY minus BX. Now note how it's done. It is A times Y multiplying B plus B minus B times X. Okay, so keep that in mind. Keep that in mind. Okay, so now this is the geometric approach in solving this kind of first order differential equation. So all you have to keep in mind is that, and in the next video I'm going to explain how the coordinate method also can be employed to solve this kind of first order differential equations. Please leave a like on this video and subscribe to the channel, and don't forget to turn on post notifications. And yeah, see you in the next video. Bye.